One of the faculty members received prestigious Professor Narasimha Endowment Award for his research activities from Savitribai Phule Pune University. UGC awarded Research Award to one of the faculty members of Chemistry Department. Every year, Chemistry Department celebrates National Science Day. In this year, on the occasion of National Science Day, Chemistry Department organized the online guest lecture on the topic Nucleophilic Substitution Reactions. Great academician and eminent scientist, Professor Dr. Srinivas Hota sir from Indian Institute of Science, Education and Research, ISER, will deliver the lecture on this topic. I welcome Professor Dr. Srinivas Hota sir for this event and request all of you to enjoy this lecture. With these few words, I am handovering this charge of this event to Dr. Agassi, and I am requesting her to give the introduction of Professor Dr. Srinivas Hota sir. Thank you very much. Agassi madam.
Yes, sir. Good morning, one and all. It gives me immense pleasure to introduce our today's speaker, Honorable Dr. Srinivas Hota sir, renowned Professor of Chemistry from Indian Institute of Science, Education, Research, that is ISER Pune. Sir did his BSc in 1991 from Andhra University, MSc from School of Chemistry, University of Hyderabad. Sir also did MTech in Biochemical Engineering in 1995 from Varanasi and PhD in 2001 from Osmania University, Hyderabad. Sir has 20 plus years of experience in organic chemistry. He has been teaching organic chemistry, medicinal chemistry, laboratory courses for more than 15 years. Sir has started his research career in 1993 from Institute of Technology, Varanasi. He was also associated with IICT Hyderabad, NCL Pune, the Rockefeller University, New York, and now currently he is associated with the Indian Institute of Science, Education and Research, Pune. Sir has to his credit around 6 patents and 77 publications in national and international journals with 2,387 number of citations. Around 15 students has been awarded PhD degree under his guidance so far. He has also guided number of undergraduate and postgraduate students for their research projects. Currently, sir is leading a research group of 10 PhD students and 4 postdoctorate students. Sir has generated financial support of around 12 crore over the last 15 years from all the major leading funding agencies of India. Sir has visited around 15 countries and addressed 25 international and 124 national symposia. Sir received n number of awards till date. The few of them are Department of Atomic Energy Young Scientist Research Award, RSC West India Section Young Scientist Award, NCL Research Foundation Scientist Award, AVRA Foundation Young Scientist Award, CDRI Award for Excellence in Drug Research, and so on. Sir is also a life member of Chemical Research Society of India, that is CRSI, and was a member of Royal Society of Chemistry. Sir is also a member of Board of Studies of the Department of Chemistry, Baroda University, Gujarat. Today, sir will be delivering a lecture on the topic Nucleophilic Substitution Reactions. It will be a great treat and lifetime achievement for we all to listen to you, sir. And on behalf of the Department of Chemistry, once again, I welcome you, sir, for the today's lecture on the occasion of the National Science Day. And I request you to please start your session.
Sir, please unmute you.
Okay. Sorry.
Yeah.
Yeah. Now I'm okay?
Yes, sir.
Okay. So let me start sharing now. Okay. You have to stop sharing, then I will be able to share my slides. Yes. Can you see my slides now? Can you see my slides?
Yes, sir.
Yes, sir.
Okay. Okay. So just one second, because we stop seeing once we see the screen. Okay. Thank you very much, Dr. Agashe, for that kind introduction, though I do not actually deserve so many kind words and all. And before I start, what I wanted to say today, actually, I would like to thank Professor Vivek Bobde for extending the invitation to be part of your National Science Day celebrations. And I also shall be indebted to Professor Sanjeevan Kharath for keeping the stage ready for me to take on, because today happens to be the National Science Day. And why are we celebrating? He has nicely said that, but to reiterate, I think I would again say that on this day in 1928, this particular phenomena of the so-called Raman effect has been declared to the public, and because of which we all have been enlightened, and at the same time we have been ecstatic about the so-called Raman effect that was discovered in about 1928. And for that phenomenal thing, Professor Sir C.V. Raman received the Nobel Prize in 1930. There were a lot of stories about this particular winning of the Nobel Prize in 1930 before even Nobel Prize got announced. Sir C.V. Raman has booked his ticket, because those days he has to travel by sea, and for which tickets may not be available. So he was so sure that he will be winning the Nobel Prize in 1930. That's the kind of scientific contribution and confidence and the kind of work that he did while working in Indian Institute of, now today it is known as IACS, Indian Association for Cultivation of Science. And today, even after almost like 96 years or 94 years or so, even today, there are almost like every single institution of eminence has a Raman spectrometer, which is very important for characterizing variety of molecules. In ICER itself, we have a couple of them, and then there are Raman microscopes, there are Raman spectrometers, and then which give fantastic information which otherwise is not very easy to obtain. Okay. Having said that, now what is the inference from here? There are 2 or 3 things, because majority of you are undergraduate, even the BSc or MSc students of this great organization called HYK, whatever, HPT Arts and RYK Science College in Nashik. This discovery happened in that IACS in Calcutta. But if you look at, the whole world is looking towards the west now instead of east. So if you draw a line from Calcutta and in the western direction with some exactly, it will be falling into the range of Nashik. Okay, so Nashik, Pune, Mumbai, and this region. And with the great academics and with the great teachers such as Bobade, Kharath, and Agashe, and so many people, I think it's not too far away from winning another Nobel Prize in India, for India, by Indians very soon. Okay, so that should happen from the western side of the country. That's my wish. Okay, and at the same time, you're all rightly positioned to take up such kind of challenges that will be winning laurels for the country, because the country is literally in like a desert for winning the Nobel Prizes. So this is the first ever Nobel Prize that any Indian has won. But of course, one can argue that at that point of time, we were a colonial, we were ruled by Britishers. So in principle or in practice, if you call, this Nobel Prize also goes to the British ruled India. So far in science, no Indian who is working from Indian continent or Indian soil, has received a Nobel Prize in Science. So we won Nobel Prizes in peace. We won Nobel Prize in literature with, again, Tagore won that one. But that is again from the eastern side of the country. So now it's time for us to make India proud again by winning a Nobel Prize from the western side of the country. And as students of today in 2022, from the HPK Arts and RYK Science College and western region of the country, I think you have a great responsibility to make India proud again by doing significant scientific contributions. Okay, so with this, today I will be delighted because I'm delighted at the same time because there are 100 students who are participating in this meeting at this point of time. That shows your commitment to science and being part of this National Science Day 2022 celebrations. Let's not forget that we need to get yet another Nobel Prize, either in economics or in chemistry or biology or physiology or medicine, including physics, peace, and literature. I mean, there is no doubt that India has great talent, and so are you. So there is a great responsibility in every one of our shoulders to take the mantle to the highest possible thing, so that we will be able to bring back the glory of Indian mind to the world stage. With this, I would say that in my own way, in a small way, what I do is that I will try to tell you a story called nucleophilic substitutions. And for a long time, this particular one, I mean, why am I telling about this one is there is a simple reason that this is part of your syllabus. And at the same time, I mean, your teachers are telling so many things about these kinds of nucleophilic substitution mechanisms. And I also teach the same thing at IISER Pune for the students who actually enter into our program after 10+2. And what I'm trying to tell you is the same lecture that I give for my students or the students who enroll in my class. And so bear with me that this will be the very fundamental thing. But of course, if you look at even Raman's contribution to the science, it's so fundamental. So that means that we need to be strong in fundamentals so that we will be able to understand what is their intricacies. There was one great question. I mean, I tell you what is the question that student asked me about 10 days back in the class. I mean, the kind of question that he had asked me is still intriguing. I mean, so India has talent, but we are unable to nurture that talent at this point of time. I think the government of India is taking a lot of steps in order to nurture. So I think we shall make use of such kind of things and do whatever is possible in every possible manner. Okay, so the reaction that you're quite familiar with is something like this, where benzoyl chloride, if you treat with amine, it becomes benzamide. Okay. So then one can ask a question like, how is it happening? I mean, so we all know that there is some fundamental thing which is available with ammonia, and then we all know that it's a nucleophile, and at the same time it has got a lone pair of electrons. So that means that it will be able to donate that electron to something which can actually attract those electrons or take that electron. And then this pair of electrons will be pushing towards the most electrophilic center in this particular benzoyl chloride, which happens to be the carbonyl. And then it pushes the electrons towards the oxygen. And then it becomes O- and N+, and then finally proton intramolecularly gets transferred. And we get a more stable neutral species, which is nothing but aminol or whatever you call it. And at the same time, after that, what will happen is the nitrogen still has again gained the lone pair, and because of which it can now push the electrons. Now this time it becomes not the carbonyl, but now the weakest bond happens to be the carbon chloride bond. So because of this particular bond leaves, and the Cl- leaves, and we will be able to get iminium ion. And this iminium ion is now next to an alcohol, so because of which deprotonation can happen, and ultimately we'll be able to get benzamide. When I explained this one, so there was one student called Deeksha who asked me a question saying that
ऐसे हमारा वो जो HOD है उसकी बहुत पहचान है.
Oh, well, yeah. Man, what can we do? Yeah, we cannot do anything if your HOD does not know Python.
मैं लड़कियां देख रहा था.
Yeah. But money alone is not sufficient to do science, of course. Yeah. So one student called as Deep Shah has actually asked me one question.
Profession से जो तबाही है ना बंदी का उसकी आंखें ग्रे ग्रे.
Oh, somebody is, I mean, am I disturbing somebody or?
ट्राउजर ठीक है लूज वाला और एकदम टाइट टी शर्ट और बेल्ट.
Yeah, now I'm fine. Yeah, so what happened is that, sir, is it hypothetical that our arrow pushing mechanism that we see, can we really see these electrons? Or is it only hypothetically we say that? That's a beautiful question. That's a great, I mean, he could ask that question, dare to ask that question, but there is a Nobel Prize in that one, that particular question. The question is, can we see electrons? Okay, and we all know that Heisenberg's uncertainty principle says that we cannot locate the position of electrons and its momentum at this point of time. Maybe at some point of time in the evolution, maybe somebody would be able to debunk Heisenberg's uncertainty principle, saying that, hey, Heisenberg, you sleep now. I'm raising from my bed. So. But I said that one, but at the same time, I was not very sure about the answer that I gave. So I looked at the literature, and then if you see, there are a couple of people who are working on such kind of a problem, like how to debunk the Heisenberg uncertainty principle. If somebody actually does that, brings a proof for identifying the electron and its momentum at the same time, then there are a lot of things which can get, we get better handle on how to view at mechanisms. So that is going to be a great thing. And that's a great question from Deep Shah in my class of last week. Okay, so in this particular process, what are these things? One is a nucleophile and there is a leaving group. Okay, so why am I telling the name and person is this Deep Shah is just joined BSc, but the kind of question that he came up with is very good, but he has to work on that problem for a long period of time to bring it to a fruition. And I'm telling you, revealing that particular question to you because you can offer a solution to that, and let's there be a positive competition between Deep Shah versus the 100 participants who are here. Okay, including me. I'm not denying that. Okay, so the nucleophile which will be attacking, and then the leaving, there is something called chlorine which is leaving from this particular molecule. So this leaving group can leave. And in this situation, what is the most important thing that has to happen? There are a few lessons that we should learn. One is that there is an attacking agent and there is something which is leaving. And these two have to be in synchronization with each other. Otherwise, it will be leading to a lot of problems. For example, if the nucleophile is very inert and it's not going to do anything and it's just sitting in the reaction medium, and the leaving group is very fast and then it is very aggressive. I mean, it has got great propensity to leave. What is happening is that because right now all of you are asked to attend this one, otherwise you won't get attendance or something. So you will all be here. And the moment you are out, immediately you will get out and then you will not even bother about what is the nucleophile substitution and all these things. If that is the kind of thing, then the nucleophile cannot attack on that one. And at the same time, if the nucleophile is very aggressive and the chloride is not leaving, then again it's not a good situation. Or if both are actually matching in terms of their ability to attack and the ability to leave from there, then what is going to happen is it's a perfect situation for the reaction to happen. And where the reaction happens, there will be a round bottom flask where you will add benzoyl chloride and ammonia. And in that particular round bottom flask, the magic happens. And you will be able to see that magic, and you will be able to characterize this benzamide from the reaction flask that you have, which is in this case, it happens to be the round bottom flask. So how do we write this entire thing? Normally in some of the popular textbooks of Indian authors and some of the foreign authors also write like this, but this I feel that this is not the right way to write it, because the ammonia is not attacking and chlorine is not the one which is leaving, but the first thing is the most electrophilic center is the carbonyl, so it attacks and then electron push actions towards the oxygen and comes back, and then chloride will be able to leave, and because of which we will be seeing that the net transformation, one can actually simplify this, but to make it correct, and as I said, this particular kind of thing will be debunked only when we see whether it is happening this way or this way. It will be happening only after somebody debunks Heisenberg's uncertainty principle. Until that time, it's better for us to write in this particular fashion rather than this way, because this is much more correct arrow pushing mechanism. So now, so then somebody has asked a question to the system, saying that what if, I said that the electrons are, the lone pair of electrons are attacking on the most electrophilic center. This happens to be the carbonyl in the benzoyl chloride case here. And what will happen if I don't have the most electrophilic center? So in this case, now what can happen? So that means that I will be removing this carbonyl group from here. So which is nothing but two vertical lines and one oxygen here. And if I remove that, what is going to happen to the molecule? So now a trigonal carbon has become a tetrahedral carbon. Okay, so what? So if you ask me that question, then I would say that, okay, the tetrahedral carbon, and we all know that if you have 4 different substitutions on a tetrahedral carbon, it can become chiral. So what is so important about chiral? The next question comes. The question is, there are n number of examples where the tetrahedral carbon with 4 different substitutions or a chiral compound is shown to be, one of the enantiomer was shown to be useful for bringing out a kind of property that we want, whereas the other isomer sometimes could become a problematic thing. So now in this case, we call this as benzyl group, BenZyl, and whereas this one is a benzoyl group, which is nothing but BenZOYl, and just oxygen insertion, so BenZOYl. For a long time as a student, I used to get confused between pH and benzyl, because the pH is known as benzene, whereas benzyl means you have another additional CH2 here. Okay, this particular red thing is called as benzyl. So now, because I don't have a very good electrophilic system in the molecule, so now what will happen is that the nucleophile needs to be much more stronger than ammonia, and the strength of the nucleophile, in fact, has to make it something like an anion. So in this case, I'm showing with thiolate because it is present as the same thing in the Clayden's book, so it becomes easy for you to follow. And this particular thiolate will now be attacking on this, and then chlorine can depart. So as you notice that because of the less amount of reactivity, I am now using a much more aggressive nucleophile compared to the ammonia. In this case, ammonia and this particular molecule are in sync with each other, because of which we will be able to do the reaction. Whereas here, the nucleophile is needed to be much more stronger. So if you look at this nucleophilic substitution at the saturated carbon, now I am coming from unsaturated carbon to a saturated carbon, there are 2 possibilities for the mechanism. One is that the chloride can leave as it is, and because now the chloride is a good leaving group from here because of the electron withdrawing nature of the chlorine. And once this happens, then we will be able to get a carbocation. Okay. Now, once you have the carbocation, now because it is stabilized, because also that pH, your teachers, maybe Professor Brobre or Professor Karat or Professor Jyoti or somebody must have told you definitely that benzylic carbocations are very stable. And because of which now this molecule has become a flat one, because now it's no longer an sp3 carbon. Now it has become an sp2 situation, because of which it's a flat one, and there is a p orbital which can be attacked by the thiolate either from the top phase or from the bottom phase to get you this compound. In this particular scenario of benzyl chloride, there is no problem of the top phase or re phase and C phase, but if I show you this particular one, just by replacing this hydrogen with a CH3 group, now I am making this particular molecule as a chiral one. And if it is chiral, now once you get a flat intermediate like this, maybe CH3 is here. So because of which, then what will happen is thiolate can attack from either the top face to give us the R isomer, or from the bottom face so that we will be able to get the S isomer. So that means that starting from one compound, you are destroying the chirality of the molecule, and because of which, so it's not a good situation, because you're starting with one compound and you are resulting into two compounds, and at the same time, your teachers definitely must have told you that enantiomers cannot be separated by any physical means. So that means that this particular one will be possibility one will be giving us a kind of two molecules. Okay. So now what is the possibility two? The two can work in sync with each other. That means that if the chloride is leaving from here, the thiolate is coming from this side. And that means that we have a situation where the attacking group and the leaving group will be at 180 degrees with each other. So that means that it is coming from here and the leaving group is going from there. So what is the situation here? So then there was another guy who has asked another beautiful question. Sir, isn't it going to be a pentavalent carbon? Yes, in principle it is. But what will happen is that in practice it is not, because as this is moving, let's say it comes 2 millimeter close to this carbon center. So then it is leaving from there by 2 millimeters. So that means that net bond order will be equal, maintained as a tetrahedral carbon, but the reactive intermediate at some point of time it will be shown as a pentavalent one, but it is all about one has to look at these things by taking into account the wave nature of the molecule, because the thiolate is a wave and chloride is another wave. So this wave is leaving, and it's all orbital interactions that are driving the reaction force. Okay. And then the question that is posed, and then the way I explain that one is, right now, if you see, there is a war or a kind of situation between Ukraine and Russia. So there is a Russian president and then there is a Ukrainian president. These two guys are not fighting with each other. Who are fighting? The foot level soldiers. Okay, the soldiers are the solvent molecules in the round bottom flask. And the two presidents are, one is this benzyl chloride and the other one is the thiolate. Okay, so once the reorientation of the solvent molecules or soldiers do enough amount of work on the ground, then only the bonds will form. Okay, so here this particular thing is facilitated by the solvent molecules to make it ready for the attack and for chloride to leave from there. So because of which this reaction happens. So suppose if I do with the same molecule that I have shown you here, this reaction, if the possibility 2 is correct, then I shall be able to get, because the attack is happening from the backside of 180 degrees to this chlorine. So because of which I shall be able to get only the S isomer. If you see here, I will be getting 2 molecules which are nothing but enantiomeric pairs. But now all of a sudden I started seeing only 1. Okay. Now, which of these 2 mechanisms are going to operate? And that needs to be worked out. And then the number of questions that we can ask in this particular 2 possibilities is, how do we detect the carbocation? And how do we prove that this particular reaction is following through the possibility 1 and not the possibility number 2? Okay, so if that is the case, I mean, just to show you an analogy, it is like this. This cat is nicely sleeping, and whereas the tiger is waiting there. Okay, so because it's more considerate one and then very mellowed down, and it is waiting until this cat leaves from its place so that now the tiger can sleep there. Whereas now this tiger is frowning because it wants to take rest, and at the same time it is not really okay for a bigger animal like tiger to wait for a cat to leave from the den. So because of which now it is attacking, so that another cat has to immediately get out from there and then keep watching the tiger to enjoy the life. Okay, so these are the 2 possibilities. Now what is our job is, now in the next 5-10 minutes we have to find out how this, whether this happens or this happens, and how do we confirm the presence of this particular term. In this case it happens to be the carbocation or not. Okay. Now, having seen that, now rate of reaction, how do we find that? So whether the carbocation is forming or carbocation is not forming, that's the question. So carbocations, we all know that if we put 3 electron donating groups onto that one, so that the charge will be stabilized, because of which it will be able to form in a easier manner, and then it will be increasing the lifetime of that particular carbocation. This we know that. I mean, definitely, because from basic chemistry, we all understand that if you have a tertiary butyl group, because of the presence of 3 hydroxy groups, so then what the 3 methyl groups, what will happen? So it is going to stabilize the carbon with the carbocation, so that we'll be able to now attack the bromide from this side. Whereas if you have the same thing, another isomer of this one, which is nothing but butanol, if you add HBr, then what is going to happen is H plus will be protonating this, so that OH minus is not a very good leaving group. So H plus has to protonate, and then this departs, and then bromine can come. Whereas here in this case, H plus will protonate, and then Br can attack on this, and H2O can leave from here. And we also, this is what is the intermediate that it will form. In this case, there will be no intermediate. You must have been taught by your teachers, Professor Bobbade, Professor Karat, or Professor Jyoti Agashe, and all these people, that if the charge is next to a kind of unsaturated carbon, what will happen is it will have more resonance structures, because of which it is going to be stable. So now the stable or unstable is a relative term. Let's understand that first. Okay. Now, so what do we mean by that? It's a stable means, can I see that one in a bottle? Or this one, it is unstable. Or in this case, butanol with a positive charge. That's it. So I'm saying that butanol, if it forms a carbocation, then this is more stable, I'm saying. So more stable or less stable means what? And this question was asked by this man called George Wohler. Okay, so he was working in Hungary, and he felt, I mean, everybody talks about these carbocations, and nobody has a proof. Nobody has seen this carbocation. So now, it's, how many of you have asked that question to yourself? I never asked myself until I read about this particular guy called George Wohler. Okay, so my teacher told me that tertiary butyl carbocation is stable. Why is it stable? Because they told me that a methyl group is pumping around. But then they say that after that, sometimes allylic carbocation is more stable, or benzylic carbocation is more stable. Now, what is the story? So, which one is the most stable? And what is the relative stability of this? And can I see these carbocations? This is the kind of question that he asked to himself, and tried probing this one. How he did it? And that formed the basic for his winning the Nobel Prize in 1994, for his pioneering contributions to and proving that carbocations are indeed present. How he did it is like this. Now, earlier we thought that, okay, H plus is going to protonate this. So that means that F, or something like in the previous case, it will be bromine minus. And here, if this is getting protonated, F minus is coming. Now, if I take this F minus out from that one, so now what happens, F minus, so you require something that takes the fluoride ion. And that happened to be from the literature reports, this Hungarian has found that pentafluoroantimonate is right for that, so that it will become SbF6 minus, which is known to stabilize. Today, there are several salts which are available in the market which have got this SbF6 minus. And suppose we also use in our lab silver hexafluoroantimonate. And it's most importantly, it's a non-nucleophilic anion. And if this is there, then what will happen is, now I am going to make it, now because of the electrostatic interaction, the lifetime of the species is going to be much more. So it gives me room for me to spectroscopically, similar to what Raman has developed. There may be other spectrometers which are also possible. And by spectroscopic means, I shall be able to detect this species, because if I don't add, I have SbF6 minus, then immediately this tertiary butyl group will be attacked by the F minus without leaving any time for me to detect. So now what happened by adding this SbF5, so it forms a hexafluoroantimonate, and this hexafluoroantimonate is now electrostatically stabilizing. It is increasing the stability of this tertiary butyl group, and because of which the lifetime of the species got increased, And that enabled him to do a few spectroscopic experiments, and also that it's a non-nucleophilic anion. That means that, and in addition, it does not have any kind of protons on this particular one. So that is actually a boon for him. And this is from the Nobel Prize website. So this particular picture, and if you go to this nobelprize.org and then write George Wohler, and you will see a nice write-up about how he came out and how he got that question, and then why he used HF pyridine, and so much of information is there in this particular website. Instead of doing your Facebook, YouTube, and then all those movies and all, you just go to nobelprize.org, and I strongly encourage you to read their Nobel lectures. Every year they release around December the Nobel lectures, and these give. You see, a lot of times while we are teaching, we will be telling you what is the discovery and what it is. But we will not be telling you because of the time restrictions and then because of our own problems of teaching and then other responsibilities. So we are unable to teach you how they came up with this particular idea of solving carbocations, or why did they think about working on the carbocations, and then a lot of things. I mean, this particular website gives you a lot of information. I mean, if you go through Nobel lecture by lecture, I think you are going to enjoy the chemistry or maybe the scientific enterprise. If you are majoring in chemistry, I strongly encourage you to go to this website and then see the chemistry Nobel Prizes, and then go through year by year, either starting from the beginning or from today. If you see, I mean, every year they release it in December. So I hope that you will give some consideration to my words and go to the nobelprize.org and look at what and why, what is covered in many books, but why did they work and how did they solve that problem are not told by, it's kept as a secret because we try to learn what it is, and then by the time we grasp what it is, we lose the question of why is it important, and then how is it important, and how they have solved that particular problem. So I strongly encourage you to go to this website and then look at yourself, so that you will be able to appreciate yourself the kind of discoveries these great souls have done for the world. Okay, so in this case, what happened? Tertiary butyl cation. Okay, this is the NMR spectrum of the first time they have done that trimethyl carbenium ion. Okay, so what happens normally, you must have been taught that NMR is a kind of tool for elucidating the structure of a molecule. So normally tertiary butyl group, if you have C with C3CH3, so all of them are magnetically equivalent. So because of which the methyl groups are all equal, so I shall get 9 protons, and it should be coming around 1 ppm because it is not attached to any kind of a electronegative or no other group that can influence the magnetic field, applied magnetic field. So because of which I should see at 1 ppm. But when he recorded the NMR spectrum of that one, so he saw that at 4.2 ppm or something. And when he repeated with yet another amyl alcohol, so then he could see this kind of NMR. And when he saw that for the isopropyl, he nicely saw that about septet in the region of 13. So which means that, so there is a charge buildup. We know that one from the NMR. Okay, so that showed him to prove that when I add OH minus, I'll be able to get the carbocation, and this is stabilized by, and it can be attacked from either the top phase or backside attack, or so from the bottom phase of the molecule. And whereas in the case of butanol, why was it possible? Because the first thing is he asked that question. And at the same time, this non-nucleophilic anion, which is not going to give a signal for the NMR, but it will be stabilizing this so that it increases the lifetime of the species, so that we will be able to record the NMR spectrum. And this reaction happens to be faster than this happens to be slower, because there are 2 molecules which are involved in the molecule. And this we have seen, and then we are going to now prove that what are these numbers that we write. Substitution nucleophilic, you understood. Now about substitution nucleophilic, the 1 and 2 possibilities we have not yet. We know now that in which reaction a carbocation forms, but we still do not know the reaction that we thought about tertiary butanol reacting with HBr to give you the tertiary butyl bromide, we do not know which particular pathway it happens yet. Okay, so next, what somebody else has asked that question, and then they tried to do one experiment. They took the tertiary butyl bromide and they added OH minus to get the tertiary butanol. Let's say this is the reaction that you wish to do. And now there are two possibilities, as we thought that there is a charge buildup, tertiary butyl carbocation, and in the other case, it's a constructed one. And so what they did is that simple. You take the tertiary butyl bromide concentration and concentration you are varying, and you try to measure the rate of the reaction. So rate of the reaction, how do we find? That's a different thing. Let's worry about how you are forming this particular one. You measure this tertiary butanol, and then you will be able to plot that one, and how quickly this tertiary butanol forms for every concentration variation of this tertiary butyl bromide, and you will get this kind of a plot. And if you see that there is a slope here, and at the same time it is increasing as the tertiary butyl bromide concentration is increasing, so the rate of the reaction is increasing. Whereas if I vary the sodium hydroxide concentration, I will be measuring the rate of the reaction of formation of tertiary butanol, and the rate is not changing at all. It is more or less constant. That means that this reaction is not dependent on the concentration of the sodium hydroxide, but it is dependent only on the concentration of the tertiary butyl bromide. And that means that, and we all also know that from our physical chemistry knowledge, that rate depends on the rate limiting step, which happens to be the concentration of this particular tertiary butyl bromide and not the sodium hydroxide. So rate is equal to K1 times tertiary butyl bromide. That means that it is dependent only on the concentration of this one. That is why we write 1 here. That means that it's a unimolecular reaction. So that's why SN1 will come. Now, suppose if I take this particular one, methyl iodide and thiolate, why am I using these examples? One can also show with others also, but this is present in the Claydon so that it becomes easier for you and for me to explain. Okay, and so here, if you change the methyl iodide concentration, you're having a slope with a straight line and linearly it is increasing, we call it. And at some point of time, it is already saturated. And now if you take the sodium, what is this, sodium, thiomethyl sodium, I don't know what do you call that, methyl thiosodium, let's leave it. So this particular concentration of this particular reagent, then again we are seeing the slope. So that means that this is also having a role in the rate of the reaction, in affecting the rate of the reaction. So that means that rate is equal to K1 times, you can put K2 also if you don't like K1. So NaSMe and methyl iodide, because two compounds are involved in the rate limiting step. So we call it as bimolecular reaction, and that's how we can say that SN1 or SN2. Okay, so to sum up this one, so methyl iodide and second, primary, secondary, tertiary, quaternary. And then you have our methyl primary, secondary, tertiary, and then these two will not be favorable for the carbocation formation. Depending on what are R groups here, it may be following either of them. And here it will be definitely the carbocation. So if you have a tertiary butyl or tertiary compound, it will definitely go through the SN1. And then in these cases, it is very difficult to prove whether it is going to be SN1 or SN2. Okay. So now if we look at what is the, suppose if you have done the same thing and you are putting the, now you are trying to do with reference to the energy, how do we calculate the energy through the Arrhenius plot, and you will be able to get the energy. And if you plot that one, and then what will happen, reactants and products. Products normally will have, what is that, some amount of, what is that, gives free energy gain. And it normally has to go through a kind of a uphill task. And this can be reduced by adding catalyst and all such kind of things. And then this is the kind of thing where this intermediate will be stable for a little longer time. That means that there will be two transition states in this particular pathway of SN1, whereas this will be the intermediate. Do not forget that there is a difference between transition state and the intermediate. The subtle difference is transition states are the points where the highest energy in the energy diagram, whereas the intermediate has lesser energy compared to the transition state, and this is called the activation energy, and for this one, this will be the activation energy because it happens to be lesser than this one, so it immediately slides. But nevertheless, what Vola has done is that he pulled this one down so that it will be stable for a little longer time, so that he was able to detect this tertiary butyl carbocation. How do we look at it if it is SN2? It will be much broader. And here the transition state will be lying here somewhere, which will have all the 5 elements. But if you look at the way they have put it, and then I also reproduce the same thing here, which is even 2 dots. That means that here also there will be 2 dots, and then there will be 2 double negative and then double positive charge. Whereas the products and then all these things, it will be nicely, smoothly done. So this is how one can actually prove whether it is SN1 or SN2. Okay, now somebody has asked another question. Suppose if I now have a much more aggressive nucleophile which will be leaving, and now I can vary the nucleophile here. So acetate, chloride, phenoxide, OH minus, PHS minus. The rate of reaction has been found to be, if you see what they did, now they have changed the, what do you call this, the nucleophilicity, and then they try to measure the rate of the reaction, 3.9, 4, 3.8, 74, 107. So, and they also have been able to find out what it could be following, whether it is SN1 or SN2. So if it is acetate, they could see that SN1 it forms, and then Cl minus SN1, whereas pH minus. But when they went to the OH minus, it became SN2 because it became a much more aggressive nucleophile. So perfect synchronization is proven through this particular thing here. So whereas if you take methyl bromide, no matter what it is, because it's now actually stabilized because of the presence of this phenyl group, and it is called, as I said, it is a benzylic carbocation buildup. But still, though it is benzylic carbocation, there are cases where it will be seen as SN2. But whereas in this case, bromomethane, the no matter what nucleophile it is, because there is no charge buildup on this, unlike benzyl chloride. So we have no matter what kind of a nucleophile, the same set of nucleophiles, but the rate of the reaction is going to be the same SN2. So the numbers are not going to vary much. So what is this non-classical carbocations? So then somebody called, Herbert C. Brown came and said that if that is the case, can I make a carbocation at the bridge head? So bridge head means we all know that. And we all also know that tertiary butyl group are having the flat, I have shown you that the planar structure. So if it is going to be like this kind of a molecule, then what is going to happen? Now this is confirmed and it is conformationally restricted. So it cannot form the positive charge here. And that, how does it behave? So then, as I said, this is not going to be favorable process. And this kind of things are called as non-classical carbocations, where you have the charge delocalization, 3-centered 2-electron bond, and normal covalent bonds are 2-centered 2-electron bonds. And then because of the presence of this particular Cl, so, and again, they did Vola did that in the medium of SpF5 and fluorosulfuric acid, and this kind of a solvent he has used, and thereby he was able to stabilize this for a little longer, and at minus 65 degrees Celsius, he could identify this particular species, and whereas at minus 30, he was able to see that. But when he went to minus 90 degrees Celsius, he could definitely see that because this was all possible because of there are 2-3 things. The question that George Vola has asked, The second thing is that identification of mining the literature and getting it to the point that where F minus is suitable for him and SBF5. And the third one is the invention or discovery of or availability of the NMR for him to study with a variable temperature. And that was all facilitated because he is able to do the reaction in the pentafluoro antimonate. And likewise, he gave, these are some of the 3-center 2-electron bonds. And so now there was another one who has asked yet another question. Now these two are allylic hydroxy groups. Now what is the difference that it can form? Suppose if I do from here, now the allylic carbocation is forming here. So because of which it will form a 3-center 2-electron bonds. And now the bromide can attack from here to here, or on this particular carbon, or on this carbon. So, but they are noticing that in 80% of the cases, or 80% yield, you get only the primary allylic bromide. In 20% of the scenarios, you get secondary bromide. This also has been tested with this allylic alcohol also. Here also the same thing can form, but the net result is going to be the same. This is how many a times we prove the mechanism, saying that it is following through the carbocation formation. So what happened here? So they were at HBr basically. So HBr, H plus protonation happened, and then it gave the intermediate. Here also the protonation happened, and then they got the allylic carbocation, or 3-center 2-electron bond. And this particular one now is susceptible for this side and this side attack. You may now say that, sir, why there is a kind of 80% or 20%? The 20% comes because it is sterically demanding, because there is if it is going to be a simple allylic one similar to this 3-center 2-electron bond, then we could have got 1:1. But because of the presence of the methyl group, now Br minus will feel the steric hindrance, and because of which it will be giving us a little lesser quantity of this product compared to that. So the collision theory again works for us, where you have the attack happening from the more amount of attack happens from the terminal carbon rather than the secondary one that we have. Suppose if you do with this one, so you will be able to get complete, because dimethyl group, so you will be able to get only the attack from the least sterically demanding path of this particular allylic carbocation, and because of which we will be able to get this prenyl bromide in a much easier manner. And this is the comparison relative rate, which shows that 1 degree allylic and benzylic alcohol, and then you have dimethyl group. You see that so the kind of reaction rates that they follow are indicative that whether it is SN1 or SN2, and then I leave it to you to actually infer yourself. So what will happen? Suppose now, what will I do is now I'll keep both the leaving group and the attacking thing around the same carbon. So how will it be possible? We will see that one. Suppose now the leaving group leaves, and then you will be indirectly creating a kind of saturated one, unsaturation here, so that the nucleophile can attack, and then the same thing can happen. So X can be either OR, SR, NR, and leaving group can be chloride, bromide, H2O means it will be actually having the OH here. So when we add acid, it gets protonated, and then you will be able to see that one. So this is one of the examples where you have gem dimethyl group, which is nothing we call it as, because if R1 and R2 are alkyl group, then we call it as ketol. And if you add H plus to that, then we will be able to protonate one of them, and then the other one immediately quickly cleaves off that and then kicks it out. And because of that, you will get water addition onto that, so that now water can get protonated, and ultimately you will be able to get this kind of a thing. And these are called hemiacetals, hemiketols, okay? And suppose what will happen if I have the leaving group on the same molecule, but now on the adjacent carbon. So what is happening now? I move OH minus, which will be silver plus. Why is silver plus required? To pull this one. Okay, so OH minus is required to make it O minus here, carboxylate, and this will be attacking on the bromide. So now what should happen? the OH minus should attack on this one, and we should get, as from the previous discussions, it should attack from the backside, and because of which I shall be able to get the attack here. So I shall get the S isomer of that. Now let's see what happens here. So because this is present, so the leaving group will be going out, and Lg minus and this kind of thing is possible. So because of which you will be able to get two of them. Okay. And whereas in this case, now what is happening, OH minus has formed, silver is actually a very good one for halides. So that is pulling that off that side, and this is now favored for the attack. So because of that, now what happened, the backside attack happened. That means that 180 degrees to this, because silver is pulling that one. So now what happened, OH minus will be attacking here, and CO2 minus. So net retention of the configuration happened, because these are called double inversions. Okay, so double inversions means first inversion happened at this reaction, whereas in the next reaction of attack of the OH minus, there is another double inversion leads to the retention in the configuration. These are called neighboring group participations. Dr. Agashe, can I take another 5 minutes, or maybe this may be the last one to discuss? I think. Is it
Yes,
okay?
sir. Yes, sir. Please continue.
If students are getting bored, I can't see their faces. Yeah.
No, sir. You can continue.
I just want to say this neighboring group participation. How do we confirm the presence of or absence of neighboring group participation? Okay. So here you have now the attacking group and the leaving group are on adjacent carbons, and now the leaving group will be able to leave. And at the same time, the attacking group will be forming this kind of a attack, and thereby it will be forming dioxylenium ion. And this dioxylenium ion can now actually, the charge is delocalized between these two oxygens. And because of which, now, how do we be able to, why I said is that caught in the act, is now, if the acetic acid attacks from here, then we will be getting this product. But whereas if the acetic acid is coming from the other side, then we will be able to get the optical enantiomer of this particular molecule. In this case, it's going to be cyclohexene diol diacetate. Okay, so otherwise one can also see that there is another possibility. The acetic acid will be able to attack on this one too. Or if I can add alcohol here, I will be able to attack on this tertiary cation. So this compound also was isolated, and then how is it possible? Because of the neighboring group participation of the acetate group after the departure of the tosylate, then we will be able to get this dioxylenium ion, and the dioxylenium ion can be now trapped with the alcohol so that it becomes easier. So the same phenomena, one can use it for the benefit. So for example, if you have a epoxide like this, and then if you add H+, we know that it gets coordinated with this or protonates this oxirane oxygen, and then because of which now ethanol will be able to attack on this particular carbon, whereas if you add ethoxide, sodium ethoxide, the mechanism will be in a different fashion. So this is how the reaction is going to happen, whereas because here what is happening is that the carbocation is now forming, and then ethanol will be able to attack, and the tertiary butyl carbocation is the key here. Whereas in this case, what is happening is that this one is forming ETO minus, so because of which we will be able to get the tertiary butanol or whatever, this kind of a tertiary alcohol here. So this is what I wanted to share with all of you, the kind of excitement that one can have by making these molecules in the round bottom flask, and at the same time one should be able to do if the question is correct, then we will be able to get the correct answer. And the kind of question you ask is the thing that determines the answer that we get. If you ask a stupid question, you get a stupid answer, and then you get stupid rewards. And whereas if we ask an intelligent question, and at the same time asking the question itself is not, I mean, asking the question not in the class, to yourself, saying that what is it, Okay, how this is forming. Teacher said that, okay, this carbocation has formed. I mean, how do I detect? I mean, there could be yet another question, like what the student asked in my class, where he had asked me, is it hypothetical or we are able to see what is happening in real time? At this point of time, it's not possible, but at some point of time, it should be possible. So we should be, in a way, what we should do is we should have the great inquisitiveness, and there is nothing unusual or there is nothing great about those individuals who have done wonders, and we learn what they are doing. But the only thing that they did is that they have asked the right questions at the right time of the evolution. I'm sure that by studying in HPT Arts and RYK Science College, agnostic, and being part of this great enterprise called Indian Science, and being in western part of the country, I think you all will be able to do wonders, and then in future you will be able to give competition to Professor C.V. Raman in your own significant manner, so that Raman is still enjoying the legacy. And there should be, I mean, I feel that there should be celebration of National Science Day on 365 days. Every day there should be a celebration of science, because the moment we get 365 Nobel Prizes for science, there is no way we can stop celebrating every day. So let's wait until that happens, and let you be that lucky one to make Science Day too. With this, I will thank again Professor Bobde, Professor Krar, and Professor Agashe for giving me this opportunity to share my excitement with you guys. Thank you very much. If I have bored you, I'm sorry. If you have learned something, I mean, I'll be very happy. If you have not learned anything, at least you know now where to go for the information of where the Nobel Prize information is available, and how you can contribute to winning the Nobel Prize. Okay, thank you very much. Now, if you have any questions, I'll be very happy to answer.
Thank you, sir.
So, if students do have any questions, you can ask.
Dr. Hota sir, it was a very nice presentation.
Yeah, thank you very much, Brother Bobde. I mean, I have not done anything. I mean, you guys are teaching much better than me, but the only thing is that I just...
No, the way you have taught it, I think definitely students must have followed what we were trying to tell them.
I don't know. I mean, yeah, anyway.